Morning. I want to welcome Arafat Ali and Nigel Pickering from Washington State University. And you are in the evaluation of biofiltration media mixes for maximizing phosphorus removal. Today, if you could put your questions in the chat box, we will deal with them when the presentation is over. And I want to welcome Arafat and Nigel and the rest of you. And please go ahead. Welcome.
So I'm going to go ahead and start briefly and then hand it over to Arafat for the rest of the presentation. I'm Nigel Pickering. I'm a research associate professor at Washington State University. I'm also with the Washington Stormwater Center. This research was funded by WashDOT and Horizons Foundation, mostly by WashDOT. And it is on the topic of bioswale. So how do we improve bioswales, which use compost, and help them prevent leaking phosphorus so we can use them in more places where the watersheds are sensitive to phosphorus. So with that, I'm going to hand it over to Arafat.
Thank you. Welcome all. Good morning. So today I'm going to present the evaluation of biofiltration media mixes for maximizing phosphorus removal. I'm Mohammad Arafat Ali. So phosphorus, we know it is a limiting nutrient in most freshwater ecosystem, and it is very important for the plant growth during photosynthesis process. But due to greater urbanization and the use of excessive phosphorus, it has been seen that the excess phosphorus is going to the surface waters through stormwater runoff without proper treatment. And excessive phosphorus can cause different disadvantages into the surface waters, like algal bloom, toxic algae, or eutrophication process. The conventional stormwater biofiltration best management practices like biofiltration, bioretention cell, biofiltration swale, these are quite effective in terms of removing different contaminants, but recent research has been studied and showed that these are not quite as effective in terms of phosphorus removal. So from that perspective, of our goal and objective of this project was to evaluate the phosphorus adsorption capacity of different adsorptive materials. And we tried to provide information on phosphorus removal relevant to bioretention cell, compost amended vegetation soils, and compost amended vegetated filter strip system, as these are mostly constitutes of sand and compost. And lastly, we tried to identify a suitable biofiltration media mix for maximizing phosphorus removal from stormwater runoff by incorporating additional adsorptive material that can actually efficiently adsorb and remove phosphorus from the effluent. Now, our work plan and task was first to pre-screen different adsorbent material. Actually, we evaluated a large number of materials, so it was kind of narrowing down into 10 or 12 materials. Then the best performing materials, we try to develop adsorption isotherm curve to see their adsorption kinetics, and then we use those better performing materials by incorporating them into our media mixes and conduct column studies. And after that, there is a small scale channel studies to see their performance in soil media mixes. Now, initially we evaluated 40 different materials, which included 9 types of biochars, 13 mineral-based materials, 12 modified materials, and 6 organic materials. For initial pre-screening, we used pilot tests, which had 2-point test. In that case, we dosed the samples with 10 milligram phosphorus per liter and 100 milligram phosphorus per liter of orthophosphate. And in that solution, we mix the adsorptive materials to identify their phosphorus removal capacity. And after that, we got 12 top performing materials for which we actually developed full adsorption isotherm curve. Let's talk about briefly about the materials. We use different materials like biochar. We use Loyalton biochar, which is from forest residues. We used egg energy biochar. It is from wheat straw. Biochar genesis was from Douglas fir and other different residues. Biochar now and raw biochar were mostly leaf-based biochar. Biochar with shell and biochar with peat were the raw biochar mixed with shell and peat respectively. The lodgepole pine biochar, the raw and the doped, both were made in the biosystem engineering department in WSU. The raw biochar was conventionally. On the other hand, the lodgepole pine biochar doped, it was doped with magnesium and nitrogen to actually increase their adsorption effect. We use different mineral-based material like oyster shell, gypsum, alum, different wollastonite, different zeolite, lime, and sand. We use different modified materials such as activated alumina, different aluminum oxide, different water treatment residuals from Richland and Pasco water treatment plant. We use crab-based chitosan. We used granulated activated carbon, layered double hydroxide, iron aggregate, bold and gold. Bold and gold is kind of a mixture of sand and clay soil, and make it a kind of modified material for better different removal of contaminants. Organic material, we use different compost like yard waste compost, leaf waste compost, manure based compost. We use coconut coir and different peat. Now for adsorption isotherm, we picked 12 better performing materials, and for that, for each material we made 13 different solution of different concentration of phosphorus ranging from 0.05 milligram phosphorus per liter to 100 milligram phosphorus per liter, and we added 2 grams of adsorptive material each of the sample, and then we kept them in the mechanical shaker for 24 hours for agitation to reach the equilibrium. After that, the solution were filtered through 0.45 micrometer filtered paper, and the filtered sample were then tested to measure the remaining phosphorus in the solution using AQ400 according to the EPA 119 method to determine phosphorus. Now, the pre-screening results, as I said, that we actually dose 2 different concentration, which the one is 10 milligram phosphorus per liter and the one is 100 milligram phosphorus per liter, and we tried to see the removal efficacy of different materials. It shows that as far as biochar is concerned, we can see that egg energy and genesis biochar and the lodgepole pine biochar, you can see that these were better performing both in 10 milligram concentration and also in 100 milligram concentration, but other raw biochars were not performed well in this case. As far as mineral based material is concerned, wollastonite fine, that material, it actually performed well in terms of phosphorus removal. Oyster shell did not perform well initially, but it performed really well when the concentration was 100 milligram phosphorus per liter in the solution. Now, the modified material, chitosan, different water treatment residuals, layered double hydroxide, activated alumina, and iron aggregate, they all perform well in terms of phosphorus removal in pilot test of pre-screening. the sand, compost, and organic matter, you can see that no compost or sand or any other organic material did not perform well. We need to especially see that here, that we combine the compost and the sand results here, because sand and compost are the primary constituents of the conventional bioretention cell. So here we can easily state that the compost and sand, they cannot actually efficiently remove phosphorus through adsorption process. So that's why the conventional bioretention cell are not quite effective in terms of phosphorus removal. Now, from these 40 materials, we picked 12 good performing materials, and we developed the full adsorption isotherm curve to see their initial phosphorus adsorption rate and also the maximum phosphorus adsorption capacity per milligram of solvent. You can see the y-axis shows the per milligram of phosphorus adsorption by per milligram of solvent. On the other hand, the x-axis shows the remaining phosphorus in the solution. Now, after that, we picked 8 different materials for column studies. For column studies, we used 26-inch depth and 6 diameter of PVC pipe. The media mix depth was 18-inch. We used glass beads at the bottom of 3-inch depth. We had rain head at the top, and the water was delivered from the top, and the effluent was taken in the bottom for sampling. This is the setup in our lab of columns. You can see 12 columns were running at a time. Now we conducted 2 experiments. One is flushing experiment and the one is dosing experiment. For flushing experiments, we actually try to evaluate the potential of phosphorus leaching from our column at the initial stage. And for dosing, we actually try to evaluate the phosphorus adsorption capacity of our soil media mix. We use 1 control and 8 treatment media mix, and we made duplicate of each, which indicates 18 soil columns. We use peristaltic pump to deliver approximately 12-inch per hour rate of water in each column. Now, for flushing, we use deionized water, and for dosing, we use synthetic stormwater dosed with 0.5 milligram phosphorus per liter concentration. For flushing, we use 10 flushing events, each were 1 hour time span, and for dosing, we use 30 dosing events, 30 rain events. Now, as far as media composition is concerned, the control was 60% sand and 40% compost per volume by volume. It is the conventional bioretention composition. And for treatment, we use 60% sand and 20% compost and 20% adsorptive additive material. We also use 80% sand and 20% compost. Now, up to this day, we have the complete flushing and dosing results of control with activated alumina additive media mixes, alum-based water treatment residual media mixes, and LDH mixed media mixes. And the others are currently in running, and we are hopeful to complete all the dosing experiments by the end of this month. Now, if we see the column flushing experiments, it's clearly, you can see that there is control. One is mixed with activated alumina, one is mixed with water treatment residual, alum-based water treatment residuals, and one mixed with LDH. Now, you can see that the control, which consists of 60% sand and 40% compost, it leaches significant amount of phosphorus in the flushing events, and compared to the control, the others, it leaches very insignificant amount of phosphorus initially, and the leaching of the phosphorus becomes almost zero at the end of the flushing experiments. From this, we can state that the phosphorus, the 40% phosphorus in the conventional bioretention system can cause significant leaching of phosphorus in surface water. Now, as far as dosing experiment is concerned, as I said before, we dose the synthetic stormwater with 0.5 milligram phosphorus per liter, and you can see that the control, it could not actually remove the phosphorus from the influent. On the other hand, the 3 other treatment media mixes, they effectively remove the phosphorus from the influent, and among the 3, you can see the alum-based water treatment residual and the activated alumina, they perform even better. So from that thing, we will move to small-scale soil study. It's an ongoing project, kind of extension of our column study. After completing all the dosing experiments from our column study, we'll have a clear and bigger scenario which materials perform best in our column study. So for activated alumina and water treatment residual perform really well. So we will pick up 2 top materials from our column study, and we will test them in a small scale channel soil study. In that case, we will use 1 control and 2 treatments, and we will use triplicates for each. For soil, we will have 6-inch depth of compost and material mix at the top, and after that there will be 3-inch topsoil. And that time we will use synthetic stormwater dosed with nutrients and metals, which includes phosphorus, nitrogen, copper, and zinc. Now, in summary, so far we have evaluated 40 materials ranging from biochars to minerals to organic materials, sands, and compost, and we have found that 12 materials that actually perform really well in terms of phosphorus removal. And we also found that compost and sand, which are the major constituents of the conventional base management practices, they do not perform well in terms of phosphorus adsorption. From our column study, we have found that compost is a significant source of phosphorus leaching, which is mostly due to the organic degradation of the compost. So far, our column study suggests that the addition of different additive materials can certainly increase the phosphorus removal efficacy. And after completing the bioswale channel study, we will be hopeful to propose feasible biofiltration media mixes with additive materials that will be feasible to effectively remove phosphorus removal from stormwater runoff. Thank you.
That's great. Thank you, Arafat. So you have a question here from Doug. Why are you using 10 and 100 milligrams per liter concentrations for influent when field values are more in the range of 0.1 to 0.5, and that is the tape influent range for total phosphorus? So if you could address that.
Okay. It was initially we had 40 materials, and for that we actually tried to narrow down from 40 to 10 materials or 20 materials. So in that case, we actually use 10 and 100 milligram phosphorus per liter to actually see their performance. But after that, in both the adsorption isotherm and the column study, we for adsorption we range from 0.05 milligram phosphorus per liter to 100 milligram phosphorus per liter to get their adsorption capacity. And in column study, we use the tape according to the tape, we use 0.5 milligram phosphorus per liter. The 100 milligram was, to identify their maximum adsorption capacity of phosphorus adsorption.
Yeah, I can add to that too. If you're looking at an adsorption isotherm, an ideal one is one that is steep. That means it works at low concentrations and also has a very high maximum where it flattens out. And so we were trying to see if we could even see what the maximum was. And in some of the materials, like the magnesium doped biochar, we didn't even come close to the maximum. So it was just a way of bracketing the two performance criteria. We'd look at the slope in the beginning and the maximum, which gives the maximum gives an idea of capacity. So, okay.
Great, thank you. Next one's pretty easy. Are most or all of the materials you're using readily available and not too expensive?
I can address that. I think we have a range of different materials. Definitely, the water treatment residuals are the cheapest because they're generally given away at this stage. Most water treatment plants have sludge they have to cart off to the landfill. So it's a good option because it's actually recycling of the material. And then we go all the way to something like LDH, the layered double hydroxyl, which is made by Sassel in Germany. And it was very effective at removing selenium. And a collaborator of ours suggested we just try it, and so we did. So that one would be very expensive. So our final choices are based on both effectiveness and availability. So we'll be looking for our final swale mixes. We'll be looking at materials that have both those characteristics.
Thank you. That was very helpful. Why is the AA material better than the WTR and LDH if AA leaches more phosphorus in the effluent?
Maybe you could go back to that slide. Can you do that? You're muted, Arafat.
Okay.
Arafat, you're still unmuted. You're still muted.
Yeah,
Arafat.
I just,
There you
yeah, go. I just shared this screen again. Yeah.
There you go. Thank you.
Are you talking about this slide?
They can't. They're all muted. So why don't you just see if you can address the question without a response?
Okay. The alum sludge and the alum sludge based water treatment residual and activated alumina, they both performed well in both adsorption isotherm curve, in also column study, better than the LDH. The thing is that the LDH is better adsorption, a better adsorptive material, but it's kind of selective for different anions. So in terms of selectivity, the phosphorus it absorb phosphorus, but not as the way efficiently that activated alumina or water treatment residual did.
Okay. Thank you, Arafat. And did you consider biosolids compost as a material in the media mixture?
Yeah, biosolid compost, like manure-based compost.
I can answer that. We did. Biosolids is generally from wastewater, and it's, as far as I know, not allowed in both the permits, both the East and the Washington permits. Doug Howie's, yes, you could probably comment. In Eastern Washington, they're allowed to use manure-based compost, but not in Western Washington. So that's why we added that. And but we didn't consider biosolid-based compost.
Yeah, good question. What are the top two most effective additive materials?
Arafat, that's you.
Thank you. So far, we have performed 3 different additive materials in column study. Among them, obviously, the activated alumina and treatment residual performed really well. But if we go back to the adsorption isotherm, we can see that there are some other very good performing materials are there, like the magnesium nitrogen doped biochar, also wollastonite. The problem is that the magnesium nitrogen doped biochar, it was actually produced in the laboratory based, and it's not actually industrial based and readily available for large amount of field work for making a conventional bioswale. So, and also we have tried wollastonite. The hydraulic conductivity was very low. The water was submerged in our column study, so we had to stop using that. So there were some things apart from only adsorption that we needed to consider in our experiments. And from that point of view, so far the results we have in our hand, activated alumina and the water treatment residual, alum-based water treatment residuals are the best 2 additives for for using in column study and biofiltration media mixes.
Okay, thank you. And for the bioswale test, is there a design flow that you'll be introducing to the swales, like 2-5 year? How will the performance vary with volume, weather, or would this be for a future study?
Okay.
Yeah, I can tackle that. We'll be using the a 6-month storm, the water quality storm, 6-month, 24-hour storm, and scaled to these small channels. It's a bit of a tricky process to get something that works. And then we also have to worry about the hydraulic retention time. In a full 100-foot swell, you're targeting 9 minutes of retention time. So that's the surface flow. So we would have to scale that back because ours are way smaller than that. So, but basically we're looking at water quality events primarily, because those are the ones that would be do most of, should do about 90% of the runoff.
Okay, thank you, Nigel. How do the materials perform at lower phosphorus concentrations that are more consistent with what is expected in stormwater?
I think you maybe the question is a little confusing. We used in the screening really high concentrations to get an idea what had really good potential. In the column studies, we're using the maximum that tape allows, which is 0.5 milligrams per liter. And that's a much more realistic number. So I think in the column study, once we finish with all the column studies, we will have more realistic estimates. And some of the ones in the adsorption isotherms that were good didn't perform exactly the same in the column. So that's why we're doing those.
Okay. This will be the last question. We'll have to wrap up. Thank you. Will you follow tape protocols with your field tests? This includes TSS removal?
Oh, absolutely. Yeah, we just we'll do the full gamut of tape tests, tape water quality parameters in the field situation, and that's a plan that WashDOT wants to do, to take the best material from this study and take it to a field scale so they can get approval through the tape process.
And then there is time for one last one. What was the source of WTRs from, and what was the percentage of solids of the sludge? And so this is coming from one of our Canadian comrades.
Arafat, you can answer the source.
Source of WTRs.
So we actually use 2 different water treatment residuals. One is alum based and one is PSCl based. We get those water treatment residuals from Richland and Pasco drinking water treatment plants.
Okay.
Yeah, just to emphasize, these are water treatment plants, not wastewater treatment plants.
Yes, water treatment plants, drinking water treatment plants.
Thank you. Thank you both very much. That was very interesting. I'm afraid we're going to have to close at this time, but it was great to have you and everyone else. And we'll see you soon. Thank you.
Bye-bye.
Thank you.
Thank you.